Hey guys, in this video we're going to talk about section 6.1, vectors in the plane. Now I will start this out by saying if you are AP, then this is technically not something that's going to be tested on the actual AP test. However, it is still something that is important for us to learn for your future math. So we're going to make sure that we cover it because it's definitely an important topic. Now, it's very likely that if you have taken a physics class, it's very likely that you've learned a lot of the information that I'm going to talk about in here. But you might have learned it in a little bit of a different way or not exactly the same terminology or notation that we're going to use here. The vectors we're going to deal with, this is vectors for precalculus. So again, if you have learned about vectors in the past, it may have looked a little bit different than what we see here. So the idea of what a vector is, and you can see some definitions up here on the screen. The idea of what a vector is it's a way kind of to show the force of something. So when you see like a car driving down the road, right? It's got a direction that it's going, and it also has a speed. And that speed is something that we can call a magnitude. Now, magnitude is not just a speed. Sometimes it can be some other kind of force, like the weight of something. So there's several different ways that we can see magnitude as long as it is a force that is acting on something. So it is a very much physics idea, but again, we are doing our little pre-calculus version of this. So one way that we can see vectors represented is we can see them represented as an ordered pair. What you're seeing on your screen right in here is the way that we would denote that. I want you to notice that these are not parentheses on either side. This is A, B with these little pointy brackets on each side, and that's very important that you use the correct notation, okay? The A is considered the horizontal component, and B is considered the vertical component. So just real quick, I'm going to kind of give you like a little sketch. Let me find something to draw on. I didn't think about this before. Aha. Okay, I'm going to give you a little sketch of what a vector can look like, just like in space. Not outer space, just in a space. But a vector can be something that starts with like a little initial point, and then it's going to go in a certain direction. Okay, so our initial point is the starting point. The terminal point is where it ends. And the direction in which it takes to get there, that can show you those horizontal and vertical components that I'm talking about. So if you look from the initial to the terminal, we have this horizontal aspect here. And then to get there, we also have this vertical aspect. Okay. Now, if you notice, this does make a little right triangle. We're going to come back to that idea in just a moment. But yes, we end up with this little horizontal vertical components from the initial to the terminal point. So that's what A and B represent. Okay. Here we go. A vector has both what? Magnitude and direction. Magnitude is what I was talking about with like a car going down the road, right? Magnitude is talking about like the speed at which the car is going. Direction talks about the direction, okay? The way we represent this is with an arrow, or some of you may think of that as a ray if you're really familiar with your geometry. Okay, let's talk about what magnitude and direction are a little bit more. So while we see magnitude, like in a real life aspect, we see magnitude as like a speed or a weight, some kind of force, right? The way we're going to see it on like a coordinate plane is you're going to see it as like the length of the arrow. So if I was looking here at my little picture, the magnitude is the length that I have between the initial and that terminal point. Okay, we denote it with these little bars on either side. See, this is a V with a ray on top, so that shows a vector V. But we put those little bars on either side. That does not mean absolute value here. It means magnitude. Direction, again, is the direction that it's going to go in. The directed angle, you may see it as this angle in here. We will talk about in a later video how to calculate that angle. So definitely look out for that one. That will not be in this video. but it will be maybe in the next one. All right, we got those pieces. Let's talk about these little notes. Again, remember how I said the initial point is going to be that first one. The terminal point is the second one. If I'm going to denote my vector this way, the initial has to be the first one shown. The terminal has to be the second one shown. The arrow has to point to the right. That is just a standard procedure for how you would name it. Okay. Keep in mind that does not mean that it will always be from left to right. So this happens to be R and S in this situation. But what if my vector was different? What if my vector went from here to here? Well, if in that case, the R and the S kind of switch which side they're on, right? The R is supposed to come from the initial side, which happens to be the point. S is supposed to go on the terminal side. So you see how you're not always going to be showing this from left to right. You have to think from initial to terminal. Okay. All right. And our other one here, this idea just says if two arrows that represent the same vector can be equivalent. So if you see that they have both the same magnitude in the same direction, then you're going to see that they are equivalent. All right. You think of two cars going down the road that are like side by side, going at the same speed. They've got the same direction. They got the same magnitude. They are technically equivalent. And you will see that they would have the exact same A and B components. Right? Remember, A is talking about the horizontal component, B is talking about the vertical. Well, if they had the same length for the magnitude and the same direction, that A and the B would be the same. So if you saw your vector in component form, they would be the same. All right, we got another rule here, and then we got an example we're going to actually work. So the head minus tail rule is something that we're going to follow. If you don't have it in component form, it can be helpful to put your vector in component form. So you'll see here, they've said that an arrow has an initial point, x1, y1, and a terminal point, x2, y2. It represents the vector, and then here is showing you the component form. I want you to think about it, though. If I take this vector that I've been talking about, and if I were to say, okay, I want to know what the A and the B are. If I want to know what the A and the B are, for A, I just need to see what the difference between the X's are between R and S. If you look at the difference between their X values, that's going to give you the A because that's the horizontal change. If you want to find the B value, you would look at the difference between their Y values from R to S, and that gives you the vertical change, and that's B. So look here. For the component form, do you see how they've got x2 minus x1 and y2 minus y1? That's just showing you the difference in your x's, the difference in your y's, and that gives you the horizontal and the vertical components. All right, I've done a lot of talking and not a lot of mathing, so we're going to do some math now. Example 1, it says to prove that the arrow from R to S is equivalent to the arrow from P to Q. So let's try a problem. What I want to show here is I want to show that they're going to have the same components if I put it in component form. I have not shown you how to find magnitude. I have not shown you how to find direction. All we've talked about up to this point is how we write vectors, what the different parts mean, and I gave you the head minus tail rule. Okay, so what we're going to do is we're going to use that head minus tail rule so that I can figure out the component form of these vectors. If I can see that they have the same components, that means that they are equivalent because they will have the same magnitude in the same direction. I've talked a lot. Okay, let's see here. We've got the vector RS. Make sure you're being careful with notation. I know that's a little tedious, but it's important that we put the initial point, then the terminal point, turn your arrow to the right. We're also using these little pointy brackets, and we're going to take, for our R and S, we're going to do the x2 minus the x1. So that's a -1 minus a -4. And minus a negative is going to cause that to become positive. So I'm going to go ahead and write it that way because I like it better. We're also going to do y2 minus y1, so 6 minus 2. And then close that off. We have used the head minus tail rule, but now we need to clean it up a little bit. So this component here, negative 1 plus 4 is 3. 6 minus 2 is 4. And there is the component form for the vector rs. Let's look at PQ. Same thing, we're using that same notation, but P and Q. And then we're going to do this same process. We're going to do the x2 minus x1, so 5 minus 2. Then y2 minus y1, 3 minus a negative 1. And minus a negative, again, I go ahead and write it as plus. 5 minus 2 is 3. 3 plus 1 is 4. Look at that. Both of these, when I found the component form, I can see that they are from the initial to the terminal point. They go to the right 3 and up 4. So they have the exact same length. They're going to have the exact same direction. These are going to be the same just as long as they were just in different positions. Okay, so I'm going to add an extra note for you just so that you can have this when you're looking back at stuff. We're going to say, although they are in different positions, they are still equivalent. Okay. All right, time to talk a little bit more about magnitude. I haven't actually talked to you about how to calculate magnitude. All we've done at this point is to really see what component form of a vector is, and that can help if we're needing to see if two vectors are equivalent, like what we saw here. It can help you knowing what that's going to look like, but it doesn't really find much else at this moment. So what I really should do now is talk about more about what magnitude is and how to find it. I'm going to bring back my little scenario that I had before with this little vector that I drew. Okay. And I want to talk about what magnitude would really be, because magnitude, remember how we said magnitude is the length of an arrow? So if I wanted to find the length of this arrow, I want you to take a moment and think about what you could do. You may come up with, there's two different options as to how you can find the length of the vector rs, right? That would be your magnitude. One way, and this is probably what most people have been coming up with first, one way to find the length of this is to do Pythagorean theorem. A squared plus b squared equals rs squared, right? You can find the length of this side by using Pythagorean theorem. That is only if you know the components. If you know A and you know B, then absolutely you can use the Pythagorean theorem. But what if you don't know A and B? What if instead, like our last problem, we were given the initial and terminal sides? What if we were given the point R and the point S? How would you find the length of this? And that goes back to a geometry thing, finding the length of a segment, right? And that would be by using distance formula. So you have two options here: Pythagorean theorem if you know your components, or distance formula if you know the initial and the terminal points. So here that is in note form. Okay, we've got more on magnitude down here. And you'll see that we've got those two kind of drawn out. I'll zoom in a little bit more. All right, so you're seeing in this first option, what if I have the components, or if I have the, not components, but the initial and the terminal points? If I've been given coordinates like that, then I can find the magnitude easily by using the distance formula. But maybe I've been given the components instead. And if I've been given the components instead, then using Pythagorean theorem will work. Now, again, this is Pythagorean theorem, a little bit tweaked just to make it a little bit of a shortcut. But that's where this comes from, a squared plus b squared, right? So the problem that we see down here, example 2, it says to find the magnitude. Find the magnitude of PQ, where P is negative 3, 4, and Q is negative 5, 2. So we're going to use our formula for magnitude for that, but we need to decide which formula that is. Because I've been given the initial and the terminal points, then I think it's going to be easiest to just straightforward use the distance formula. Now, some people will tell me, why don't you just find the a and the b and then use this one? You can. It does the exact same thing. So you choose, but I'm going to use the distance formula because I think it seems simpler. So for the distance formula, we will use P as the x1, y1, and we're going to use Q as the x2, y2. When we plug these into the formula, make sure you use your big fat square root, right? But we're going to take our -5, then minus a -3, which makes +3. Then we're going to take 2 minus 4, and then we just clean that up. -5 plus 3 is a -2. 2 minus 4, -2. Avoid using a calculator, guys, because a lot of times I'm seeing we keep typing it in wrong when we use a calculator here. So just use your brain. It's going to be safer. So when you calculate this, -2 squared should be a +4, right? If you did use a calculator, you have to put parentheses around it or it's not going to work. But we should get +4 for both of those, and then we add them together, make square root of 8. Simplify that, and it becomes 2 square root of 2. Okay? And there's our magnitude. If it asked you to put it as a decimal, then you could put it as a decimal, but this is honestly preferable in my opinion. All right, y'all, we are going to, I'm trying to decide if I want to stop. I think I'm going to pause this here, and then you will see probably 2 more videos to wrap up this section. I'm planning on taking 3 days to get through it. So we're going to try to break this up 1 day at a time. So anyways, I think we're going to stop here and then pick up with the vector operations in the next one. All right, I will see you guys in the next one. Bye.